speaker. Looks like a good time for that. Okay, so our next speaker is Professor Rebecca Gieseking from Brandeis University in Massachusetts, and she'll be talking about the integration of INDO spectroscopy models into MOPAC and her work with INDO-based spectroscopy.
Okay, well, it's been a great discussion, and I think some of this ended up that my talk is a little bit fortuitously timed because I do actually have some comparisons to DFT. So this is going to be a little different because we are focusing on excited states, which is something that really hasn't come up. So INDO and ZINDO have come up in passing a few times, but that's really going to be the focus of this talk. So just a little bit of general introduction. Most of the methods in MOPAC are these NDDO methods, and INDO is a little bit different formalism. So it has fewer of your two-center, two-electron integrals actually explicitly included. It also has certain parameters that are identical for S and P orbitals, which is not the case for a lot of your NDDO methods. And this INDO-S parametrization, also known as ZINDO or ZINDO-S, was really intended specifically for excited state properties. The parameters, because they're for excited state properties, they're really not suitable for geometry optimizations. There are a number of variations out there. So the code that I incorporated into MOPAC came from Jeffrey Reimer's CNDO INDO code. So basically, when I was adding this, I took his code and interfaced it with MOPAC. So a lot of the subroutines that are really setting up all those integrals are from his original code. And advantages of this method for excited states. As for all our semi-empirical methods, really computational cost is the big one. And especially computational cost, not just going to large systems, but going to hundreds of excited states or more. That's something that gets to be really difficult to do with any other method. We've been talking about TDDFT and self-interaction error, and so that's also a big advantage here, especially for things like charge transfer excited states. And another big advantage is that because it's CI-based, it's really easy to go beyond single excitations. TDDFT, your standard implementations are really singly excited. But with these CI methods, you can incorporate double excitations or even higher, really on an equal footing with your single excitations. The code from Jeffrey Reimer's does have two different CI algorithms, one that only handles CIS and one that handles anything with multiple excitations. So if you go beyond the single excitations, it does slow down the calculations some, but it's semi-empirical, it's still pretty fast. So just an example of going to a large system. So this is F-choranine with 162 atoms and looking at some different parameter choices. So on the top, it's changing the active space, and on the bottom, it's changing the size of the CI matrix. So by default, this code does basically a truncated single CI where it limits the size of the CI matrix. So it picks, I believe the default is 2000, and so the lowest energy 2000 excitations are included in the CI matrix. You diagonalize it once and get your energies from that. So you're not doing any sort of Davidson iterations or things like that that also add to the computational time. That also does mean that you want your CI matrix to be significantly larger than the number of excited states that you want to use. So in practice, for relatively large numbers of excited states, usually what we've seen in practice is as long as your CI matrix is 3 or 4 times as large as the number of excited states you're actually considering, things seem converged well enough. And then I have just a little bit on here about what are the keywords to do those things. So applying this to some actual examples. So one of the cases where double excitations are really crucial are your polyenes. So your first two excited states in these linear polyenes are your 2BU state, which is 90–95% plus just a HOMO to LUMO excitation, and this 1AG state that's a linear combination of three different excitations, one of which is a double HOMO to LUMO excitation. And if you get to more than octatetraene, then this 1AG state actually ends up being your first excited state. So here I have at the top the high-level reference data, this CASPT2 reference data, and you can see at 8 atoms, you get this crossover between your 1BU and your 2AG states. And if you do TDDFT with B3-LIP, this 2AG state is significantly overestimated in energy because you're not capturing that double excitation character. That double excitation character is somewhere in that 20 to 30% type range, and so leaving it out has a very large effect. INDO CIS, of course, is going to also have the same failing, but if we go to CISD or MRCI, various ways of including these higher level excitations, then we get much, much better behavior. You get those two states that are much closer in energy. And then with the MRCI, we actually do get that crossover between the 1BU and the 2AG states. So in this case, we get the crossover at 10 atoms instead of 8, but for a calculation that's sub 6 minutes compared to, I don't want to know how many hours for your CASPT2, I think that's still pretty good performance. Another reason that I was interested in this is implicit solvation. So for the ground states, INDO just borrows the COSMO code that was already in MOPAC. And then for excited states, I added in state-specific perturbative corrections. So this was originally developed by CLAMPed and implemented here. So basically, you end up with two ways that your excited state energy changes because of solvation. One term is just because you have your ground state being different, and you have that static presence of the solvent surrounding your ground state. But you also have the response of the solvent to your excited state electron density and to the change in that density when you excite the system. That change is actually related to a different dielectric constant because it's really related just to the electronic changes in the solvent, at least if you're looking at the absorption spectrum, your solvatochromism in the absorption spectrum. So that's related to refractive index squared instead of the dielectric constant. And so how this is implemented, we set up the CI matrix, we add solvent corrections for each of those excitations along the diagonal terms. We diagonalize that to get the excited states, and then we basically remove the solvent corrections for the excited states and add them back in, just to make sure that if we have states that have different amounts of charge transfer than the component excitations, that everything is added in a little more consistent way. And so by doing this, we're able to get solvatochromic shifts that are fairly reasonable. So the omega B97XD DFT functional gives fairly reasonable results. CIS works fairly well, and overall, the INDO results are relatively consistent with those. In this particular case, B3-LIP actually fails miserably. It gives extremely small solvatochromic shifts. I don't have a great answer to why that is, but it is interesting that we are getting such good results with the semi-empirical. Another case where I think the semi-empirical methods are really powerful is nonlinear optics. This is actually where I started using semi-empirical methods as a grad student. is looking at these INDO-CI excited states for systems where the double excitations were really essential. So the third order polarizability has two parts. So the real part is related to the nonlinear refractive index. So how does the refractive index change with the intensity of light? The imaginary part is related to two-photon absorption. And the expression has these three terms. I'm not going to go through it in detail. A lot of times this dipolar term is small. It's related to change in dipole moment when you excite from ground state to your excited state. The two-photon term relates to, basically, we have these series of states. So we go from the ground state to a one-photon allowed absorbing state. And then we go from the one-photon allowed state to a two-photon allowed state. And so those two-photon states a lot of times have really significant double excitation character. And then this negative term is really just related to your one-photon states. And so I have a series of molecules for this. So these are, again, these linear conjugated type molecules. And if we look at just the excited state energies, INDO-CIS works better than the methods that incorporate higher order excitations than singles. And that's not particularly surprising because when this was parametrized, the parameters were developed for CIS calculations. Really, when you add in these higher level excitations, we end up stabilizing the ground state too much, and the excited state energies end up looking higher because your ground state ends up being lower in energy. And so based on that, we expect the negative term of the third order polarizability to be relatively accurate, even for INDO-CIS. But if you look at the overall picture, the experimental is always positive. INDO-CIS for two of these three molecules actually gives you a negative third order polarizability. So your refractive index is changing in the wrong direction with the intensity of light. If you add in higher order excitations, then you get the correct sign because you have these double excitations that are really essential for these two-photon excited states. So that gives some broad sense of the capability, and I wanted to finish off with a little bit of where my group specifically is using this. So we're focused primarily on metal clusters and understanding the excited state properties and working towards understanding the dynamics of these systems. So classically, if you have a metal cluster, then metal clusters will support what are called plasmons, which are these collective coherent oscillations of the conduction electrons when light is applied to them. And so silver and gold are your most common plasmonic metals. And quantum mechanically, we've spent a lot of time working on how do we define this. And basically what we see is that you have this absorption peak that is really analogous to what you see for the classical systems. And if you look at that state, you end up with this linear combination of all kinds of different excitations contributing to your one mean absorbing state. So it's collective because we have all of these different single excitations contributing, and then it's coherent because they're mostly contributing to the transition dipole moment in the same direction. So what I showed you on the previous slide was TDDFT work, but we were able to parametrize INDO to give absorption spectra very similar to what you get from TDDFT. And again, coming back to this theme of lots of excited states, this main absorbing peak isn't just that, oh, we're getting our first excited state energy, right? That main absorbing peak is really around your 50th excited state or so. And so we're correctly getting that you have a bunch of low energy states that are not strongly absorbing, and then this main absorption peak. We're also working on developing parameters for gold and making sure that things are working for ligand protected clusters, not just the bare metal clusters as well. And coming back to double excitations, one of the questions from the early DFT work was, if a plasmon is collective, then are single excitations really good enough? And that was something that from TDDFT, you really can't answer. And so by doing INDO CISD, we were able to come back and answer this question. So here I have two examples of a silver 13 cluster with very different charges. So if we have a really large positive charge on it, then our main absorbing state is around 4.5 EV. And that's just so low in energy that you can't have any double excitations contributing to that state. If you go to the negatively charged cluster, then your main absorbing state is a little over 4 EV, where we have that red square. And so we have lots of double excitations that are energetically accessible. But your main absorbing plasmon-like state is basically just single excitations, even though the double excitations are energetically accessible. So this helps confirm that in a lot of cases, really a single excitation picture is good enough for describing these plasmon-like states. We do see when we go from INDO-CIS to INDO-CISD that we do get some pretty significant shifts in that absorption peak, but that's really coming from double excitations, in this case, getting you better treatment of the ground state and not of the excited state. Coming back full circle to the main methods that we've been talking about today, we've also been working on parametrizing PM7 for metals. And this is a case where the experimental reference data is really lacking. And so we generated a bunch of coupled cluster reference data, and we're able to reparametrize and get binding energies that are basically as close to coupled cluster as you would expect DFT to get. So in summary, I think this INDO-S is a really powerful and underappreciated method for a number of things. States with doubly excited character, it's a really powerful method of at least getting reasonable results very quickly. For things like nonlinear optics, where hundreds of excited states are important, it's also really helpful, and I showed a couple applications for that as well. And then I think these extensions to metals are also a place where we have really large systems, and we can do some really interesting things with semi-empirical methods that would be difficult to do using any other methods. So I'd like to thank my group. So I've got a postdoc, Gieseking, who's currently doing some of the INDO parameterization, and a grad student, Shiwei, who's been working on the PM7 parameterization, and the funding from PRF and NSF. I'd be happy to answer questions.
Great. Thank you for your talk, Rebecca. Does anyone have any questions for Rebecca?
I don't know how to raise my hand, but hopefully you can hear me. This is Joe Leonard.
Yeah.
My question for the two of you, you and Rebecca, is this in your copy of Open MOPAC or her copy of Open MOPAC, or both?
What are you referring to? Just the INDO spectroscopy?
The stuff that was talking about. I mean, there was the statement of things I put in MOPAC. And having worked academia a long time ago, we had our version of codes that were different than other groups' versions of codes, even though it was purportedly the same code. And so I guess what I'm wondering is if there was code modifications, where all do they exist right now?
So this was all incorporated into the public release.
Cool. Okay. Thank you.
The INDO features were contributed, when was it 2021? Was that the?
I believe I did most of that in 2020. Yeah.
But then I guess you were speaking about new PM7 parameterization, so that's not in that.
Yeah, the parameters, you would have to go to our paper and put in the parameters into a parameter file.
Okay. No, we had a request, one of our customers asked about UV visible spectra. And I remembered INDO from ancient times when Mike Zerner's group was writing it. And, so I saw something was in, but then this seems to be either where it came from or a much newer implementation, which is good to know. Thank you.
Hi, Rebecca. Can you hear me?
Yeah, someone has
Yes.
their hand. Is this Alexi Markin?
Oh,
No.
no, sorry. I didn't raise my hand.
Oh, okay. Alexi Markin has their hand raised.
Okay,
Maybe
sure.
you take their question, then take your question.
Can you hear me?
Yes.
Yes.
Oh, okay. Rebecca, thanks a lot for your nice presentation. And it's maybe not a question, but a deep wish. Please also implement in your parametrization set copper, because for surface enhanced Raman spectroscopy, for which I'm working with, it's really very important. And then we will have full set copper, silver, gold, and it would be really, really great, because from practical point of view, I believe that copper will be very useful. So
Yeah, I agree.
yeah.
And copper is something that we've done the DFT optimizations to get the base clusters. We haven't started doing any of the coupled cluster calculations on them, but that's something that we definitely have in mind.
Okay, thank you.
Okay. So now to the person who started to ask a question, who I interrupted. Sorry about that.
Oh, that's totally fine. My fault. Really nice talk, Rebecca. I'm wondering what kind of diagonalization routine is used in the code.
So I didn't touch, so like for diagonalizing the CI matrix?
Yeah.
Yeah, so I didn't touch any of the code that was there from what Jeffrey Reimers had. As far as I understand, it's just setting up the entire matrix and doing the complete diagonalization. So it's not doing any sort of sparse matrices or partial diagonalization. It's just diagonalizing the entire matrix.
Oh, it seems like it's direct diagonalization, not a Davidson routine in subspace, right?
Correct. Yes.
Okay, I see. Thank you.
Are there any other questions? If not, oh wait, there's one more question.
I'm sorry, but I can't lose a chance to ask you. Have you tried some computations of source with
Yes.
MOPAC code, and were they successful?
Yeah, we actually have, I didn't have time to show that today, but we actually have at least 3 or 4 papers on SIRS. And so we have been able to do quite a bit of that.
Okay, thanks.
Okay, all right. So now we'll move on to our next speaker.